Hello, I am Beyza Sayracı. Today I will tell you about the work I have done on my graduation project. The name of my graduation project is COVID-19 Detection from Large Computed Tomography Image with Artificial Intelligence Based Interface, and my academic supervisor is LOBE. First of all, I will tell you about my context section. In the first part, I will talk about my motivation. In the second part, I will give information about the COVID project. We conduct studies using UNet and deep laboratory in deep learning models, which are part of artificial intelligence. We carried out our study named COVID-19 Detection from Lung Computed Tomography Image with Artificial Intelligence-Based Interface using Convolution Neural Networks. Finally, I will tell you about the results we have achieved up to this point and the custom designed desktop application called DeepChestNet. First of all, I would like to talk about my motivation for my graduation project. COVID-19 is a virus outbreak that emerged on December 1, 2019 in Wuhan, China. It spread to the whole world in a short time and became a major epidemic and was declared a pandemic by the World Health Organization. A large number of cases and deaths have also been observed in our country. The virus has mutated, resulting in different variants. As a result of these variants, the rate of spread increased and started to produce more deadly results. There are multiple methods to reduce the number of patients and deaths. Some of these are wearing masks, paying attention on hygiene, getting vaccinated, staying at home, keeping distance of 1.5 meters, and minimizing interaction with people. The most important of these methods is early diagnosis. Polymerase chain reaction is used in the early diagnosis of diseases due to the late results of the PCR test and its low reliability. The radiologists also prefer computed tomography, which is a radiologic imaging method. However, eye fatigue resulting from long working hours in specialist radiologists may cause the patient to be misdiagnosed. COVID-19 can cause delays and errors in the diagnosis process. These disadvantages can have vital consequences for a patient during the pandemic period. In order to prevent the increasing number of cases and deaths, there is a need for a system that can assist healthcare professionals in diagnosis COVID-19. For this purpose, the project aims to develop an automatic system that can diagnose artificial intelligence-based COVID-19. The second step is to prepare the datasets to be used in the trainings using deep learning models. First, the lung segmentation. Dataset 1034 value on the left. In the images which are in the lung mask PNG 1034 dataset are used to generate the dataset. The images are not cropped, but they are only resized by 256. Training and test ratio %80 and %20 respectively. Secondly, the dataset is augmented by using 1034 images, which is selected major code area from the original DCOM and convex PNG dataset. So we get 7038 images. Each image is cropped according to size, training, and text ratio are %18 and %20 respectively. The dataset used for LOBE segmentation was created by multiplying the original image of these images with the image images resulting from lung segmentation. Our third part consists of the methods we will apply for the determined work pages. The project consists of 3 work pages, or first page is lung segmentation and lobe segmentation. Our second page is COVID segmentation, and our third page consists of determining the type of COVID in the lung. The datasets we create were formed as output after passing through lung, COVID, and lobe segmentation as input, scenes images, and output images. The method is divided into 2. The first step is lung segmentation. Our aim is to segment lung region in the original image. The architecture used in this step developed WAL3. Developed WAL3 is a semantic segmentation architecture. The architecture consists of 2 parts, encoder and decoder. In the encoder part, we apply dimension reduction for feature maps. We have abstract convolution, which is called related convolution. In the decoder part, we increase dimension of the feature maps. VGG or ResNet, which is deep learning architecture, are used with convolution to downsampling the feature maps. Let's see architecture which is used in the developed WAL3. The first of these is ResNet. The second of these is VGG16. And the last of these is VGG19. The general representation of the system design using the developed WAL3 model is as follows. This is original image and this is lung segmentation image. The second step is COVID segmentation. The aim is detection of COVID regions. UNet architecture is used in this step. The architecture consists of 2 parts, encoder and decoder. The decoder part contains of convolution and max pooling layer. Aim of the encoder part is dimension reduction for feature maps. The decoder part contains convolution, upconvolution, and max pooling layer. Aim of the decoder part increase dimension of the feature maps. UNet is that there are a large number of feature channels in the upsampling part, which allows the network to propagate context information to higher resolution layers. The general representation of the system designed using the UNet model is as follows. This is lung segmented image, this is COVID segmented image. The third step is lobe segmentation. The aim is to identify the lobes of the lung. The UNet model was also used in the lobe segmentation steps. The dataset resulting from lung segmentation and original dataset were multiplied as inputs. This is lobe segmented image. Final step is findings. The aim is identifying the type of COVID. Looking for ground glass opacity in each lobe, the GGO found 4 bilateral right-left lung segment, right-left lung information, multilobar information on which how many lobes, and for focal number of GGO in the lobe. Our fourth part is custom designed desktop application called chestnut. Here is a demo video up to the point where this chestnut was developed. First of all, there is a login screen where doctors can log in with a username and password. Now, give a username, right, and password, right. And click login button. Then the main screen seen to appears. First of all, the patient folder is selected with the select image button. And then various CT images of the patient appears. Doctors can select desired CT image and look at on the screens as a scene. Doctor click the predict button to see whether the patient is COVID-19 or not. This is select right screen and you see is predict lung. Here doctors can examine the patient's lobes by sliding the lobe slider. You can also access information about the lobes and the COVID in the information box at the top left. By sliding the COVID slider, a doctor can see the COVID area on the CT scan. You can get information about the area occupied by the COVID in the lunch. You can learn the type of the COVID with the information box in the upper right. This is and others CT images in the folder, and you prepare single slider and see CT images, and you get information about lobes and the COVID in information boxes at the top left, and can learn the type of the COVID in the right information. This is deep chestnut desktop application. Fifth steps is to examine the results we have obtained as a result of the trainings. As a result of the dataset used in lung segmentation training was carried out with more than one CNN architecture, you can see their composition in table. ResUnit and DeepLab Vol3 plus ResNet architectures show the best results. For COVID segmentation, as a result of the dataset used in COVID segmentation, training was carried out with more than one CNN architecture. You can see their composition in table. ResUnit architecture showed the best results. As a result of the dataset used in lobe segmentation, training was carried out with more than one CNN architecture. You can see their composition in table. Unit architecture showed the best results. Finally, we will review our conclusion and I will share the work. In lung segmentation, the lung region in the chest CT image was separated from the non-lung pixel via CNN-based architecture using the lab sub-datasets. The lung segmentation task aims to increase the region of interest of the lung region. The CNN-based architectures UNet, ResUnit, and DeepLab Vol3 Plus, which contain ResNet 50, VGG16, and VGG19 as a backbone, were trained using the mask in the sub-datasets to present a benchmark. For COVID segmentation, a pixel-wise separation between the infection region and background on chest CT image is called the infection segmentation task. The images belonging to the infection subdata sets were fed the input of the CNN-based architecture, RES unit, then unit, which backbones are VGG16, VGG19, and DeepLab Vol3+, which contain ResNet 50, VGG16, and VGG19 backbones were employed for the architectures. For lobe segmentation, a line consists of the right upper, right lower, left upper, left middle, and left lower lobes. The knowledge of the lobe in which an infection region helps to decide the findings of COVID-19. Therefore, the study performs the lobe segmentation task, a pixel-wise classification of 5 lobes and background to find which lobes contain an infection region. The images in the lobar subdata sets were predicted via the best trained architecture in the lung segmentation text. Then the images created by performing element-wise product between the predicted lung mask and corresponding images in the lobar subdata set were employed as the input of the CNN-based architecture. REST unit, then unit, and unit, which contains VGG16 and VGG19 as a backbone, were used as the architecture in the lobar segmentation task. Thank you for your attention.